Hi everyone, and welcome back to the mathematics course. Here's Jonathan, and today we're going to talk about lecture number 5, functions. So what is a function? A function is defined as the relation between a set of inputs having one output each. And it's really important here to mention that every input has only one output each. Okay, so it's very important, and I'll explain it later on. But that's the definition of function. Now, what about the notation? So generally we denote a function as fx or gx or hx, where the x represents the input of the function. And then we have two more definitions. The set of all inputs, it's what we call the domain, and the set of all the outputs is what we call the range. Now let's do an example. Let's say that we have a function f, and what is f exactly? So first we need to mention what is the input. So the input here, meaning the domain, the set of all the inputs, is -2, -1, 0, 1, and 2. And the output, what we call the range, is 0, 1, and 4. Now let's draw different arrows that will explain how the function works. So for example here, -2, if you plug -2 into the function, it returns 0. If you plug -1, for example, it returns 1. And if you plug 0, so let's assume that it returns 4. And if you plug 1, it returns 4. And if you plug 2, it returns 4. So another way to write it is that f of -2, so if the input is -2, that's 0. F of -1 returns 1. And so on. F of, for example, one more, f of 2 returns 4. Okay, so that's the function f. Okay, now let's look at g. So let's say that the input, again, the domain is 3, 4, and 5. And the output, the range, is 1, 2, 3, and 5. And 5. Okay. Now let's say that now we're going to draw the arrows. Okay, so the arrows define the rule of the function. And let's say that 3 is going to 1, 4 is going to 1, and 4 also is going to 2, and 5 is going to 3, and 5 also is going to 5. In this case, g isn't a function. Why? Because here you can see that for this specific input 4, we have two outputs. But we said that the definition of a function is that that's a set of inputs having one output each. So here we have two outputs for 4 and two outputs for 5. And therefore, g isn't a function in this case. So it's very important to understand each time if a specific object is a function. Now I'd like to show you another way to think about a function. So let's do it on the next slide. Many times we think of a function as a machine. Okay, so we think about a function as a machine. Let's think of the machine as f. And what f returns the input squared. So for example, if the input is 1, it returns 1 squared. And if the input is 5, it returns 5 squared. Okay. Now I'd like to add one more remark regarding the notation of a function. So we said that in general, we denote the function as f of x or g of x and so on. But there is a common way of writing a function and by using y. So for example, another way to denote function. For example, we can write y, okay, equals to 5x cubed minus 2x squared plus 3. Okay, so y replace f of x. Okay, so that's a common way to write functions. So we could also write it as fx equals to 5x cubed minus 2x squared plus 3. Okay, and this function works like that. So if, for example, you want to understand what is the output of 1, so you need to plug 1, and you'll get 5 times 1 cubed minus 2 times 1 squared plus 3. Okay, and so on. So two different ways to denote the functions. One way is to use y equals to something, and the other way is to denote it by f of x or g of x or h of x. Okay, now I like to talk about different types of function. When talking about function, in general, an interesting question is, what does a function look like? So René Descartes came with the xy coordinate system, and he proposed to take the plane and split it into 4 quadrants. How exactly? So we draw the x-axis, the y-axis, and here we have 4 quadrants. The first one, the second one, the third one, and the fourth one. And then each point here has 2 coordinates. So for example, here you'll see that x equals to 3 and y equals to 2. So the first coordinate refers to x coordinate, and the second one is the one refers to y. Okay, so for example, if I ask you, what are the coordinates here? So the coordinates are x equals to 1, and y, the height here, is 0. And if I ask you what is the coordinates of, what is the coordinate here, so you'll say that the coordinates are x equals to 0 and y equals to 4. And again, we can do it for the second quadrant, the third quadrant, so let's do one for the second quadrant. So for example, here, what is the coordinate here? Well, there are 2 coordinates, so we can ask what are the 2 coordinates x, y. So in this case, x is -2, so the first one refers to x, and the second one refers to y, meaning also 2. Okay, so that ends the idea of what René Descartes came up with, and now we are going to present different graphs of different functions. Okay, so let's continue on the next slide. Okay, so now I'd like to talk about common functions and their graphs. So the first one I'd like to present is what we call a linear function. In general, a linear function is written as y equals to mx plus n, or maybe some of you studied school in different way to write it, so maybe y equals to ax plus b. Okay, so that's basically the same, where m represents the slope or the gradient we already talked about, and n represents the intercept with y. Okay, so many times instead of using n we write b, but in the end what is important is that the number that multiplies x is the slope, and the one that doesn't depend on x is what we call the intercept. Now let's try to draw the function. So in general, the function is a straight line. So if that's x and that's y, so it can look like that, it can be like that, maybe like that, or even like that. Okay, so there are infinite ways, and everything depends on what is m and what is n. So for example, if you take the function y equals to 3x plus 5, so this function looks something like that. So here we know that 5, that's the intercept. Let's say that 5 is somewhere here. So it looks something like that. Okay. Now, also we know what is this point. Okay. This point y equals to 0, so you can compute it. So if y equals to 0, so you have 3x plus 5, meaning 3x equals to minus 5, meaning that x equals to minus 5 over 3. So this point here is this, the x here is minus 5 over 3. So that's the function y equals to 3x plus 5. Now it's very important to understand that that's not a linear function. Why? Because it's not a function. Why it's not a function? So suppose that here it's 3. Okay, it's not a function because for x equals to 3, we have infinite. And if you remember, we said that if it's a function, any input has only one output. Okay, in this case, for x equals to 3, we have, for example, y equals to 5, 6, 7, and so forth. So of course, that cannot be a function. Okay, let's continue with more common functions. Okay, so what is a parabolic function? So a parabolic function is what we call also a quadratic function. Quadratic function. And we already talked about a quadratic equation. What is a quadratic function? So a quadratic function, that's a function that is written as ax squared plus bx plus c, where a is 0. Okay, so now let's try to draw the graph of a quadratic function. So basically that depends on two things. One thing is what is a exactly. So if a is positive or a is negative. And the other thing is what about delta? So let me remind that delta, okay, delta, let me write it here, that's b squared minus 4 times ac. Okay, so let's do a small table here, and let's say what happens if delta is, let's do it in blue, so if delta is positive or 0 or negative. Okay, so let me just draw the table here. Here. Okay, one more. Here. Okay, so now when a is positive, we said that the parabolic function is smiling. Okay, so that means that it's smiling like that. Yes, so that's what we mean by a smiling parabolic function. Now, when delta is positive, we said in class that there are two solutions to the quadratic equation. That means that the function intersects with the x-axis in 2 points. So the function looks something like that. Now, if delta equals to 0, we said in class that the quadratic equation has exactly one solution. And therefore, if you draw the graph, you'll see that the parabolic function intersects with the x-axis only in 1 point. And if delta is negative, that means that there is no solution. There is no x that is solving this quadratic function. And therefore, it looks something like that. Now, if a is negative, that means that the function, the quadratic function, is what we call a set quadratic function. Looks something like that. And again, now we need to look at the different deltas. So if delta is positive, that means that we have two solutions to the quadratic function when we take this function to be equals to 0. And therefore, that means that the function intersects with the x-axis at 2 points. That means it looks something like that. And if delta equals to 0, it means that there is only one solution to the quadratic function, and therefore it looks something like that. Here we have only one point that the function intersects with. And when delta is smaller than 0, it's negative, then there is no solution to the quadratic equation, and therefore it looks something like that. Okay, so that summarizes all the different options of how a quadratic function looks in the graph. And now let's continue with the other functions. So the absolute function, so that can be written as fx equals to the absolute value of x. And we already know how the absolute value of x is defined, so it returns x if it's non-negative. Otherwise, if it's negative, it returns minus x. And how the function looks like, so let me draw it here. So something like that. Okay, x and y. So here, for example, if the input is 1, it returns 1. If the input is 2, it returns 2. And if the input is minus 1, so what is the absolute value of minus 1? Exactly 1. And minus 2? Exactly 2. And so on. So that's how the function looks like. Okay, another function I'd like to talk about is what we call exponential function. Let me do it here. So here, exponential functions. Okay. So what is an exponential function? An exponential function is defined as a to the power of x, where a needs to be positive. Okay. And now the graph itself depends on what is a. For example, if the function is y equals 2 to the power of x, it looks something like that. 2 to the power of x. But now if you take y equals to 10 to the power of x, so here it's even faster. So of course, even faster. And what happens if a equals to 1/2? So in this case, you'll see that it's something like that. 1 second. And here it intersects any of those functions at 1. Why? Because let's say that that's y equals to 1/2 to the power of x. Why? Because when x equals to 0, so everything equals to 1. So 1/2 times to the power of 0, that's 1. 10 to the power of 0, that's 1. Okay, so that's how the graph looks like. So when a is somewhere between 0 to 1, so you'll see that the graph is decreasing when x becomes bigger. But when a is somewhere between 1 to infinity, the graph is increasing. Okay, so for example, for 2, you see that it's increasing. Okay, so we talked about the exponential function, the absolute function, the linear function, the quadratic function, and now let's continue with finding the domain of a function. Okay, so let's continue on the next slide. Now I'd like to talk about finding the domain of a function. So till now we talked about 4 different functions: the linear function, quadratic functions, and absolute value, and the exponential functions. And if you notice, they are not limited by the domain. I mean, you can substitute any number and in the end get an output of each of those functions. For example, if you decide to define f of x to be 3 to the power of x exponential function, so you can substitute any number here. Okay, so for example, you can ask, what is f of 1, f of pi, f of e, f of 0, and so on. So you can substitute any number instead of x, and then get a result, an output. Okay? And that works also for the linear function and the quadratic function, the absolute value. But now the question is, what happens if the domain is restricted? What do I mean by restricted? So let's look at this example. Suppose that you decide to define g of x to be 1 over x. Now, we said that in general, we cannot divide by 0. So that means that all the domain here is everything, every number beside 0. Okay, so that means that you can plug instead of x any number beside 0, because if you plug 0, you'll get 1 over 0, and that's not defined. Okay, so that's the domain, every number beside 0. Let's do one more example. So maybe 2 more. So that's the first one. The second one, so suppose that you define the function to be the square root of 1 minus x. So we already talked about the square root, okay? And we said that everything that is written in the square root needs to be non-negative, okay? Otherwise, it's not defined. It's not well defined. So what we need to do is to say that in this case, what is the domain? So the domain that's 1 minus x needs to be bigger than or equals to 0. Okay, so that's a restriction on edge, okay? Because here, we need to be careful not to plug anything that can make 1 minus x to be negative, and therefore 1 minus x needs to be bigger than or equals to 0. So that means that 1 is bigger than or equals to x. Or another way to write it is that x is less than or equals to 1. So that means that the input here can be only a value, a number that is less than or equals to 1. Otherwise, it's not well defined. So the domain would be any value such that x is less than or equals to 1. Okay, let's do one more example. Suppose that the function is defined as 1 over x minus 1 times x minus 2 times x minus 3, and so on, times x minus 10. Okay, so now we look at the denominator and we see a product of x minus 1 times x minus 2 times x minus 3, and so on. Now we need to be careful again, because here we have a fraction. We said that in general the denominator cannot be 0. Now if you plug 1, you'll get 0 times something, that's 0. So x cannot be 1. And if you plug 2, you'll get also that it's 2 minus 1, so that's 1, times 0 times anything here in the end, that's going to be 0. So x cannot be 2. And 3, and so on till 10. So what is the domain? The domain is any value, any number, that isn't 1, 2, 3 to 10. So that is the domain in this function. Let's do one more, the next slide. Okay, suppose now that the function is the square root of the absolute value of x minus the absolute value of x plus 1. Now, again, we need to find the domain. And we said that when the function is the square root of something, everything that is in the square root needs to be non-negative. That means that in order to find the domain, we need to say that the absolute value of x minus the absolute value of x plus 1 needs to be bigger than or equals to 0. Okay, if you remember, we solved those kinds of, not really inequality, but equalities if it equals to 0. So basically we solve those types of questions. But if it's an inequality, that's kind of the same. So that's the same method that we showed in class. So let's do it one more time. So we need to find all the different x's such that if we plug it here, we'll get that that's bigger than or equals to 0. Another way to say it is that to find the solution to this inequality. So how exactly are we going to do that? So first we're going to draw an x-axis, and we're going to ask the question where does absolute value become 0. So here, only if x equals to 0. And here, only if x becomes minus 1. And here we have 3 different cases that we need to take into account. Case number 1, what happens if x is less than minus 1? Case number 2, what happens when x is between minus 1 to 0? And case number 3, what happens when x is at least 0? Okay, so now let's start with case number 1. Case number 1, let's assume that x is less than minus 1. So if x is less than minus 1, so think about taking the, for example, no, minus 100, minus 1000. Okay, so in case that x is less than minus 1, the absolute value of x is what? Equals to minus x. Why? Okay, let me just remind you the definition of the absolute value of x. The absolute value of x is defined as it returns x if x is non-negative, so meaning 0 or positive, and if x is negative, it returns minus x. So now, if x is less than minus 1, so that means that that's negative, and if it's negative, it needs to return minus x. So what do we get? We get minus x minus, now what about x plus 1? So we said that x is less than minus 1. Think about taking minus 1000, for example. Minus 1000 is less than minus 1. If you plug it here, you'll get that it's a negative number, and if it's a negative number, we need to return minus of the same thing that is written in the absolute value. So what we get here? Minus x plus 1. And that's bigger than or equals to 0. So what we get? Minus x plus 1 bigger than or equals to 0. And here we get that 1 is bigger than or equals to 0. And that's true for any x. Now here you need to be careful, because we assume that x is less than minus 1. And if we get that in the end 1 is bigger than or equals to 0, that means that for any x that you're going to choose, you'll get that 1 is bigger than or equals to 0. Now, because we are restricted by the condition here that x is less than minus 1, we need to say that it's true for any x that is less than minus 1. Okay? So that means that if you take any number that is less than minus 1 and you plug it here, you can try it. You'll see that you'll always get that it's bigger than or equals to 0. So that's solved case number 1. Let's talk about case number 2. Case number 2, we need to assume that x is between 0 to minus 1, including 0 and including minus 1. Okay. So Now, again, we need to ask ourselves, if we take an x that is somewhere between -1 to 0, for example, -1/2, and we plug it here, is x a negative number or a positive number? In this case, it's negative, and therefore we need to return -x. Okay, so -x, minus. Now, what about here? If you take -1/2, -1/2 plus 1 is positive. If it's positive, you need to return exactly what is written in the absolute value. Okay, so you get -x plus 1. And that's bigger than or equals to 0, so again we get -x, minus 1 is bigger than 0. Therefore, we get that -2x is bigger than or equals to 1. We divide by -2. Don't forget to switch the sign. You get that x is less than or equals to -1/2. Okay, so you'll get that x is less than or -1/2. Don't forget here that we are restricted by this range. Okay, here we said that x is somewhere between 0 to -1. Here we said that x is less than or equals to -1/2. That means that x is between -1/2 to -1. Okay, so if you take any number that is somewhere between -1 to -1/2, you'll see that that solves this inequality. Okay, let's continue with case number 3. So we solved case number 2. Now we continue with case number 3 on the next slide. Okay, so case number 3, we need to assume that x is bigger than 0. Now, if x is bigger than 0, the absolute value of x needs to be x, okay? Because here, according to the definition, it needs to return x. So here we have x minus. So again, assuming that x is bigger than 0, so for example, take 100. 100 plus 1, that's a positive number, and therefore it returns exactly what is written in the absolute value. So you'll get minus x plus 1 bigger than or equals to 0. And here you'll get that x minus x, that's 0, of course. Minus 1 bigger than or equals to 0, meaning that minus 1 is bigger than or equals to 0, meaning that it's false. Okay, of course, minus 1 is not bigger than 0, and therefore it's a false statement. That means that there is no solution in this case. That means that you cannot find an x that is positive such that this inequality holds. And you can try. So for example, you can plug in 10 or any number that is positive, and you'll see that this inequality doesn't hold. Okay, so let's now summarize everything that we know about the different solutions of this inequality. So from case number 1, case number 2, we know that the solution is x is less than -1, and x is between -1 to -1/2. So now we can draw an x-axis and say that if it's -1 and -1/2, so everything that is between -1 to -1/2 solves inequality, and everything that is even less than -1 solves inequality. And that means that the final answer, the solution for this inequality is any x that is less than or equals to -1/2. Okay? So if you take any value that is less than or equals to -1/2, that solves this inequality. And that means that the domain of the function is any x that is less than or equals to -1/2. Because you need to remember that in the end, the question wasn't finding the solutions to this inequality. The question was finding the domain of the function. And by asking this question, we got this sub-question. Okay? Okay, so that means that if you are asked about the domain of this function, it's any x that is less than or equals to -1/2. So now I'd like to talk about what is a monotonic function. A monotonic function is a function that is either always increasing or always decreasing. Okay, so let me give you some examples. For example, the linear function. The linear function is a monotonic function. Why? Well, you already know how the graph of a linear function looks like. So for example, if the slope is positive, so you can see here that it's an increasing function. If the slope is negative, so you'll see that in this case, the function is a decreasing function. So in general, the linear function is a monotonic function. What about the exponent, the exponential function? So that depends on a. If a is bigger than 1, so we said that it looks something like that, and that's an increasing function and monotonic function. But if it's a is somewhere between 0 to 1, so that's a decreasing function. Okay, what about the absolute value function? So we said that in this case, the graph looks something like that. So v, okay, that's not a monotonic function, because here you'll see that when x is less than 0, that's a decreasing function, and then it becomes an increasing function. So it's not always increasing or decreasing function, and therefore that's not a monotonic function. So let's just say no, a monotonic function, that's a monotonic function, that's a monotonic function. What about the quadratic function? So let's say, so let's draw, so for example, something like that. So that's not a monotonic function, because here again, you'll see that that's decreasing and then increasing. So it's not always increasing or always decreasing. Therefore, in this case, we said that the quadratic function isn't a monotonic function. So maybe later on, we're going to talk about what is the derivative exactly, and we'll see how to understand if a function is an increasing function or a decreasing function, or even if it's not a monotonic function. Okay, so let's continue. Now let's talk about composite functions. So a composite function is a combination of two functions. So let's go back to the idea of how we presented the function as a machine. So let's say that we have a function g, okay, that is defined as a linear function, 5x minus 8, and let's say that the input is 3. Okay, so the output needs to be 5 times 3 minus 8. Okay, great. Now let's say that we want to composite two functions. So we want to take a combination of two functions. So let's take the same g, 5x minus 8, and let's add another function f. Let's say that f is defined as x squared. And now let's again take as an input 3. Now if I take 3 as an input, g returns 7. Now, let's put 7 into f, then you'll get 49. Okay, so what we did, we combined those two functions together. So another way to write it is to say that we just took f, and we plug into f g of 3. Okay, because g of 3, that's exactly 5 times 3 minus 8. And that's exactly f of 7. And f of 7, that's exactly 7 squared, meaning 49. So we can always combine two functions, even more than two functions, even 3, 4, 5, 10 functions, infinite functions. Now, let's say that in general, we want to get an expression for the combination of those two functions. So here we just plug 3 and get 49. But suppose that I want to get a new function that is created by combining g and f together. So what we can do here is to say, so we want to compute f of g of x, meaning f of 5x minus 8. But f is defined as x squared, so that means that we need to take 5x minus 8, all of that squared. And we already know how to solve expand the bracket here. So that would be 25x squared minus 80x plus 64. So now, if you're giving me any x here, okay, any x, I can find you what the combination of f and g is going to return. Okay, so for example, here we just plug 3. So if you plug 3 here, you'll get also 49. Okay, please notice that. So let's write it as a remark here. If you take f and you combine it with j of x, it's not the same as taking g and combining it with f of x. Okay, and maybe I'll give you an example now so you'll see why it's not the same. Okay, so let's say that, let's switch here. Let's say that g of x equals to 2x and f of x equals to 1 of x. Now, if you take f of g of x, we'll get that that's f of 2x, and f of 2x, that's exactly, so here you can see that f of x is 1 of x, so if you change x by 2x, you'll get 1 over 2x. Now let's do the opposite. Now let's compute g of f of x. So g of f of x, that's g of 1 over x. Now, g of 1 over x here, you'll need to take what? To take g, and instead of x, you need to plug 1 over x. So you'll get 2 times 1 over x, meaning 2 over x. And here you can see that that's not the same, because here we got 1 over 2x, and here we got 2 over x. And therefore, you need to remember that, in general, f of g of x and g of f of x, that's not the same. Okay? So please notice that the order in this case matters. Okay, so that ends lecture number 5. And next, on lecture number 6, we're going to talk about the limits of functions. See you in the next lecture.